Hello everyone and welcome to this academic presentation video. My name is Sakib Molla. I am a student from the Department of Computer Science and Engineering, Southeast University, representing Section 2. My ID is 2023750. Today I have prepared this video presentation to dive deeply into my academic research titled Exploring Breast Machine Learning Model for Breast Cancer Prediction. This fundamental basis of this presentation is derived from a highly read 2025 study focusing on the Wisconsin breast cancer disease dataset. Universally known in this machine learning community as the WBCT dataset. In this video, we will serve as a conference breakdown of my research. We will not just look at surface level accuracy. We will we will discard we will dissect the medical background of breast cancer, identify the critical gap left by previous researchers, formally define our problem statement, and outline the strict scope of our study. Most importantly, I will walk you through the core mathematical foundation governing our select model from concluding with an in-depth analysis of our results. Whether you are a fellow CSE student, an academic, or just someone interested in healthcare technology, I invite you to stay with me as I speak a critical topic. Background of story. To fully get why this machine learning research is so vital, we first need to look at the medical and statistical background of this story. Let us be absolutely clear, breast cancer is not just an isolated medical issue. It remains a primary cause of mortality globally among women. To put this into a statistical perspective, back in 2021, we, the World Health Organization reported a staggering 5 lakh 8,000 deaths directly attributed to the disease, but the most horrifying statistic is the lifetime risks. Epidemiologically, data indicate that 1 in 8 women are expected to develop this disease globally at some point in their lives. And this problem is only scaling up predicted healthcare model. Forecast a 50% increase in global breast cancer by the year 2040. This means our healthcare system are going to face unpredicted load. Currently, our primary lines is defense are traditional diagnosis, pathologies such as monograms and biopsies. However, from a system efficiency standpoint, those have measured portlands. They are often highly invasive, causing significant physical and physiological trauma. They are often highly invasive, causing significant physical and psychological trauma. They are incredibly time consuming, measuring critical dates or weeks are lost just waiting for a lab result. And because human pathologists evaluate them, they are fundamentally prone to human diagnosis errors due to failure or subject misinterpretation. This is this is the very bottleneck and automatic machine learning model aim to bypass. Research care. Now, AI in healthcare is not entirely new. However, during our exhaustive literature review, we identified three massive research gaps the previous framework failed to solve. Research gap. Now, AI in healthcare is not entirely new. However, during our exhaustive literature review, we identified three massive research gaps that previous framework failed to solve. The first major gap is limitation comparison. A significant number of previous studies often focus entirely on tweaking individual model graphs. They just tested a random forest or just a support vector machine or SVM. That was massive, was a comprehensive performance benchmark across diverse algorithms on the exact time dataset. Without it, without this comparative baseline, it is significantly impossible to declare which algorithm is truly optimal for oncological data. A second gap is equable. The second gap is arguably the most dangerous data imbalance in almost all medical dataset. Health, healthy case, healthy cases drastically outnumber diseased cases. Many exciting frameworks fail to adequately address the inherent class imbalance between beginning a malignant case. If you train a model on 99% of beginning data, the algorithm simply learns to guess, begins to achieve a high accuracy, leads to high bias, lead, leading to high, leading to highly biased, leading to highly biased, virtually unless result in real clinical setting. The third gap was a profound Turing law. Machine learning models are highly dependent on their internal parameters. However, early diagnosis framework frequently suffered from a lack of symmetric hyperparameter optimization, which result in suboptimal predictive accuracy. They were essentially running highly complex model on default setting, which is unacceptable for model diagnosis. problem statement. Addressing those gaps lead us directly to the core problem statement of our research, which I define as the challenge of delayed diagnosis. As I mentioned earlier, 1 in 8 women are expected to develop the diseases globally. The core problem addressed by this specific research is the inaccuracy, the latency, and the physical inventions that are fundamentally inherent is currently early stage breast cancer detection methodology. In cancer treatment, time is the ultimate variable. High mortality rates are directly correlated. High mortality rates are directly correlated with late intervention. If a tumor is and advanced stage simply because the biopsy took too longer or a monogram was misread, the consequences are fatal. Therefore, our problem statement directly declared that there is a critical and urgent necessary to develop automated high precision computational model. Their model must be capable of assisting medical professionals in identifying malignant tumors rapidly. They are entirely bypassing the latency of traditional biopsies. We are aiming for near instantaneous, highly accurate computational second optimization. Scope of research. Before writing a single line code, we established a strict scope of research to ensure our study remain focused and significantly valid. We divide this scope into three parameters: dataset, algorithm, and matrix. First, the dataset. We decide to focus our entire study on the highly respected UCI WDBC dataset. The dataset is incredibly delayed, comprising 569 specific clinical instances. Each of those instances maps out 32 distinct health-related attributes, such as the appearance, texture, and connectivity of cell nuclei. During our initial exploratory data analysis, we found 16 instances with missing value, which we specifically address within scope or preprocessing. Second, of the algorithm to ensure comprehensive benchmark, we conduct a comparative analysis of our distinct machine learning architecture. Support vector machine or SVM, K nearest neighbors, KNN, bias, and neural network, specifically the multi-layer perceptor. For validation, we strictly utilized an $80 to $20 train the split test methodology. Third, evaluation metrics. In medical diagnosis, really socially on basic accuracy, this is mathematical trap. There our evaluation was deeply based on accuracy, perception record. FI score, and AUC ROC values to determine absolute real world reliability. Literature review. To build a reviewed methodology, we analyzed the best recent work in the domain. Let's review 4K studies that shaped our approach. In 2023, Strickland et al. Published a remarkable paper using feature engineering combined with XGBoost, achieving a 98.64% accuracy. However, there are limitations, which are short to everyone. Was that they focused heavily on feature modification rather than standardized raw data processing. Another 2023 study by Abdur M. Hege et al. Utilized a fast learning network for or if LN hitting 98.37% accuracy. Their most significant contribution was how they successfully address model overwriting in medical dataset. A crucial, a crucial lesson we incorporated. We also left a Hussein at all 2023. We conduct a comparative study of 8 basic instantly. Interestingly, the highlighted of efficiency of standard logic regression, which achieved a 99.122% accuracy in the specific setup. Finally, Russell et al. 2022 managed to push the boundary to 99.30% accuracy using a polynomial. Is their achieved is by utilizing a high complex four-layer exploratory method of optimization. While those studies are brilliant, our goal was to consolidate those isolated success into one. I, while those studies are brilliant, our goal was consolidate those isolated success into our unified comparative methodology workflow. Now, let us move to the most technical part of the presentation, our methodology workflow and data processing type. Our workflow flowed four distinct sequential steps. Step one was data collection, where we successfully handled the WBCD dataset accessed directly from the UCI repository. Step two was preprocessing, which was essential to fix the raw data as I mentioned earlier. We had missing data. This was carefully handled by the main method and randomization technique. Now we faced the class imbalance. The data had 357 begins case, but only 212 Milligan's case to fix the bias. We applied the SMOTE technique generating symmetric monitoring samples to perfectly balance the classes. Finally, we applied normalization, scaling the feature mathematically to ensure the high dimensional attribute would improperly dominated the model calculation. Then we execute our data splitting, 80% training and 20% testing set to validate the model generalization capabilities. The third was model training, involving the execution of SVM, KNN, NB, and neural network on the newly balanced dataset. The fourth was evaluation phase, focusing heavily on performance analysis using AUC, ROC, and data preprocessing. Data handling that method are most part of the randomization. Use SNOT technique, applied the balance of data, and use the normalization to ensure high quality data and demoralization attribute and data splitting, that is the 80% data training and 20% testing. Mathematical foundation. I am firmly believe that a computer scientist we must understand the mathematical behind the code. Let us briefly analyze the mathematical foundation of our model. Let's begin with the support vector machine. The core foundation of this represented as $f of x w to x plus b. Here, the fundamental goal is finding the optimal hyperplane capable of separating the beginning and Milligan's cases efficiently with a high dimensional space. The vector W is the normal vector to the hyperplane and B is the bias. Next, we have the net bias probability model. This is governed by bias theorem P C or X equal P of C by P of X. This is equation allows us to calculate the probability of class C, the diagnosis, given the feature vector X. It relies on the net assumption that the all secular features are completely independent on the anchor. Finally, the architecture that provide the most complex and most rewarding neural network MLP, a single neuron mathematical operation is defined as y equals sigmoid w x plus b. The represent feed forward multi-layer neurons. The critical component here is sigmoid representing activation foundation like sigmoid or ReLU. We utilized those foundation for non-classification, which is absolutely mandatory when dealing with the highly complex nonlinear relationship foundation in biological secular data. Result and comparison. After rigorous processing and computational tool, we arrived at our final result and comparison. The comparative analysis paint a very clear picture of model performance hierarchy at baseline, net bias, acid, and accuracy of 94.16%, moving up k nearest neighbors, KNN, showed the improved research in accuracy at 96.1%, and the support vector machine SPN diagnosed excellent classification capabilities, scoring at 97.78%. However, the absolute superior model was the neural network MLP, scoring at 97.78 accuracy. However, the absolute superior model was that the neural network MLP, which outperformed all traditional algorithms with an outstanding accuracy at of 98.13%. But accuracy is not everything. The most critical finding of our study is noted at the bottom of the result. The neural network achieving a nearest perfect AUC ROC, perfect AUC ROC score of 0.9992 for medical diagnostic. That means the MLP model has a 99.92% probability of correctly diagnosing between a malignant tumor or beginning cell. Generally, pra- practically zero false conclusion. To bring the comprehensive video presentation to the conclusion, our empirical study definitely identification neural network, specifically with MLP classifier, as the most stable and accurate model for WCDBT prediction. However, this is merely a stepping stone, transitioning those models from the laboratory in real-world clinical environment requires further rigorous development. Future work. Our roadmap for future direction include the three main pillars. First, data expansion. We must move beyond standard dataset by adding genetic data, lifestyle factor, and geographical demographic to ensure global generalizability. Second, assemble optimization. Exploring, we plan to explore advanced assemble technique like boosting algorithm combined with hyperparameter tuning to such closer to 100% true positive vote. Third, the most importantly, explainable AI. Third, the most importantly, explainable AI, XAI, and real-time app. We must develop real-time application where XAI increased clinical trust by absolute decision transparency, developing in chemical diagnosis hardware is our ultimate long-term object. We can view the primary reference that support the work on the final slide, including the foundation paper by Strickland and Russell. As this is the recorded presentation, I definitely can take live question. However, highly request to you ask a question in the YouTube comment section below, and I will make sure to respond to them in detail. Thank you for the watching, for your time, and you're interested in intersection the computer science and healthcare. Goodbye.